This problem says give a polynomial function with real coefficients of fourth degree, which has zeros 2, -3, and 3i. Assume that the lead coefficient is 5. So in order to explain how to do this, you might think about how zeros are found from a polynomial. Like, for example, if I had the function f of x equals x squared minus x minus 6, what I would do to find the zeros here is set the polynomial equal to 0. Now when we're finding zeros of a polynomial, we're looking for the x-intercepts of the thing. For this particular polynomial, the zeros are -2 and 3. But the way we determine that algebraically is to factor it, if possible. And then we would apply the zero factor law. So in order for the multiplication of these two things to be 0, it must be that x minus 3 is 0, or x plus 2 is 0. Then we could solve to reveal what the zeros actually are. So the zeros are -2 and 3, just like the graphing program had said. We're going to do this process in reverse now. If someone said that a polynomial has zeros of -2 and 3, then we could construct the polynomial by writing x minus -2 times x minus 3. What you do is you take the zeros and put them into these factors. Then you can simplify it and reconstruct the polynomial that you're looking for that has those zeros. With that concept in mind, I can construct a polynomial which has these zeros by creating 3 factors here. And then I'll just simply plug the zeros that they want into the factors. So put a 2 here, and a -3 here, and a 3i there. However, this particular question wants real coefficients, and it also wants what's called a fourth degree polynomial. So a first degree polynomial could be something like 3x. Second degree could be x squared minus x minus 6. Third degree could be a cubic function such as x cubed plus x squared plus x plus 1. And we're actually looking for fourth degree, which has to have a power of 4 on one of the variables, such as that. So this would not be enough for a fourth degree. At this point, what I have so far would only be considered third degree, because the very largest power of x that we'll get would be x times x times x. All the firsts of these binomials being multiplied would make x cubed. But we need fourth degree, which is x to the fourth. We also want real coefficients, so we don't want this -3i to end up putting an I in one of the coefficients. Okay, so if we simplify this just a little bit, we'll have x minus 2, x plus 3, and x minus 3i. But we need to multiply by one more factor in order to create fourth degree. Now, one thing that comes to mind is maybe we could multiply by x minus 3i again. But the problem with that is if we were to multiply firsts, outers, inners, and lasts, the i's would not all go away. And so we wouldn't end up with all real coefficients. So how do I know they wouldn't go away? Because we would get x squared minus 3ix minus 3ix plus 9i squared. See, the minus 3ix's would not cancel and would not go away. So what we have to do to fix this is to change the sign of one of these. If we do that, we'll end up with a plus here and a minus here. With this approach, the 3ix's would actually cancel. And so this is exactly what we need in order to achieve real coefficients. All right, now, if we were to multiply all this out, it would take quite a bit. It would be a lot of terms. But one thing is for sure, when we multiply the x times the x times the x times the x, this is the firsts of all the binomials, we're going to get x to the fourth, which is good because they wanted fourth degree, but they also want a lead coefficient of 5. And so in order to achieve that, to make sure that we end up with a lead coefficient of 5, we can put a 5 on the outside. This will ensure that our first term is going to be 5x to the fourth. Okay, now in order to check my work, I could go to symbolab.com. I'm going to choose expand here from the menu. And there we go. As we can see, the leading coefficient is 5. We do have a fourth degree polynomial, and all our coefficients are real as well.